Hello, this is Dr. Viv. I'm going to now talk about order of magnitude estimates. Oftentimes we want to find the approximate value of something in powers of 10. So there could be some number up front times 10 to the power an exponent, let's call it m. So I should emphasize that we are after this. That m is what we're after. We're not after this one. This is not important. This number up front could be something. We're going to use the IEEE convention. And the IEEE convention is that if this number is less than 5, then I'm going to think of it as 10 to the power 0. And if this number is greater than or equal to 5, then it can be thought of as an additional power of 10. Now, if it's exactly 5, then you have to make a call as to how important that calculation is. Oftentimes, it doesn't really matter. Now, there are some estimation requires some rules of exponents, so let me just quickly recall that. One is 10 to the a times 10 to the b is 10 to the a plus b. Then you have 10 to the power a divided by 10 to the power b is 10 to the a minus b. And lastly, 10 to the a to the power b is just 10 to the ab. Here a and b can be anything. All right, now one of the most important things you need to know about estimates is that there needs to be a plunge. You need to have courage to do this thing. You cannot sit around thinking all day about your estimates. So let's just take a simple example about this, size of an apple in powers of 10. So I always find this method, which I like to call the Goldilocks method. It comes from that old fable where you had a bear family, and that goes from place to place looking for a place to sleep, and then the bed that suits the little bear the best is Goldilocks bed, and that has become a phrase in science for ideal size. So let's try to find the ideal size of an apple. It always is useful to go by powers of 10. Is it 10 to the power 0 centimeters or 1 centimeter? That's about this big. Well, that's too small. We are talking about the diameter here. Not when I say size, I mean diameter. That's too small. That's about the size of a blueberry, not an apple. How about 10 to the 2 centimeters? Well, that's too big. That's actually 1 meter, and there are very few fruit that can be that big. Jackfruit comes to mind, subtropical fruit from Asia. So that's again too big. Therefore, the Goldilocks principle tells us that 10 to the 1 must be the right size for an apple. It's about 10 centimeters. If you look around, there are very few apples that actually measure 10 centimeters. One of them might, or a few of them might, but most of them are either smaller or bigger than 10. But remember the IEEE convention. If the apple is even 30 centimeters, the size of a basketball, it is still considered 1, because that 30 is 3 times 10 to the power 1, and 3 is still considered as 1. So this is about the right size. So that's the size of an apple. This is the basic principle we're going to use for estimation. As a concrete example, let's actually try to find, since I've already talked about the apple, let's try to find how many atoms there are in an apple. Now, atoms are complicated. There are hundreds of them, and apples are complicated. They're actually organic compounds inside the apple, and there's no such thing as an apple atom within quotes. So, but we're going to have to be bold in all these things. So we're going to assume that the hydrogen atom is what we're talking about. Now, from being a physicist for so long, I know certain facts about the hydrogen atom. Its size, again, by size I mean the diameter, is about 100 picometers. Now, if you look up the books, it's probably something else, like 106. I'm not sure what it is anymore, but it's something like that. That's 10 to the minus 10 meters, because a pico is 10 to the minus 12, and 100 adds 2 to that exponent, so it becomes 10 to the minus 10. So to find the number of atoms in an apple, all I would have to do is divide the volume of an apple by the volume of an hydrogen atom. Well, the volume of an apple, or the volume of anything, now we're going to assume the apple is actually spherical in shape, and atom is also spherical in shape. So volumes are proportional to the cube of the diameter. So this is going to be d apple cubed divided by d atom cubed. Now the actual factor, if you want to look at formulas, the actual formula for the volume of a sphere is pi over 6 d cubed. I'm not too interested in pi over 6 for two reasons. The first reason is I'm dividing. That's actually the main reason. So the pi over 6 in the numerator cancels with the pi over 6 in the denominator, and so you don't need that. The second reason is, even if I were just thinking about the volume and not the ratio of volumes, pi over 6, if you find out what pi is, it's about 3. 3 over 6 is half, and half is, again, 1. So we're not going to worry about pi over 6 very much. So d apple over d atom is, apple is 10 to the minus 1 meters, because 10 to, this is actually 10 to the minus 1 meter. The Goldilocks estimate of the apple's diameter. So that's 10 to the minus 1 meter divided by 10 to the minus 10 meters cubed. Observe the meters cancels out. So we have 10 to the minus 10 to the 9 here, because negative 1, using this rule of exponents, I get that, because that negative 10 becomes positive 10 when you take it upstairs, and positive 10 minus 1 is 9. I'm still cubing this. So I have 10 to the 27. So that's a pretty nice estimate. We know that there are about 10 to the 27 atoms, and that's a pretty large number. You can already see that it's about 1 mole of anything is Avogadro's number, so it's 6 times 10 to the 23, which in our language can be written as 10 to the 24. So an apple has got about 1,000 moles of material. I'll just leave it as material. And then you can get refined from here. If you're thinking of organic compounds, and you can think of an apple, on average, an atom of an apple is actually 10 hydrogen atoms, then that just means you have 100 moles of material, because I have to reduce everything by a factor of 10. So you can get more refined from this point if you wish. Let's try another couple examples. So that's the first example. I would like to try the second example, being somewhat more of a cosmic nature. Let's try to find the number of atoms in the universe. Well, that seems like a tall order. You can probably spend your whole life calculating it and get nowhere. So we have to be bold. Again, what is the universe? It's a bunch of stars and galaxies and things like that. So our solar system is our sun, planets, moons, comets, bunch of dust, asteroids, just about everything you can think of. However, what's the big daddy here? It's the sun. The sun has got so much mass that it dwarfs everything else. So really, the solar system is just the sun. So the sun, some basic fact about the sun, the mass of the sun, written like this, is 2 times 10 to the 30 kilograms. And well, the sun is mostly made up of hydrogen. There are other things too. If you ask an astronomer, they'll tell you a bunch of other things that's going on inside the sun as it burns the hydrogen. But for the most part, it's hydrogen. Okay, and so the mass of the hydrogen atom is The hydrogen atom is made up of a proton and an electron, but the electron is really light, so it's mostly the proton. So that's just one atomic mass unit, 1.6 times 10 to the minus 27 kg. Again, there's no need to really look it up. If you remember these things vaguely, that's enough. Even if you remember this as 1, you'll be fine because of the IEEE convention. So be really bold is the key. So the number of hydrogen atoms inside the sun is the first thing we calculate. That can be got by just simply finding the ratio of the masses. That's 2 over 1.6 times 10 to the 30 over 10 to the minus 27, and the kg cancels out, so I won't write that. And that's 1 according to the IEEE convention. So that's 10 to the 57. So that's an important number to have. Now at this point, you recall everything that you learned in NOVA by watching NOVA programs. In our galaxy, there's probably 400 billion stars, but 4 is less than 5, so I'll take it to be in the Milky Way galaxy. That's what our galaxy is called. There is 100 billion stars, 100 times 10 to the 9. We want to keep it clean in the first digit, and that's 10 to the 11 stars. This also takes into account some galaxies could be smaller or even larger. So again, we're back to the Goldilocks type estimate. And there are about 1 trillion galaxies if you ask the astronomers. So there's 10 to the 12 gal. So that's 1 trillion galaxies. So each galaxy has got about 10 to the 11 stars. So that's a total of, therefore, 10 to the 23 stars. Each of which has got 10 to the 57 atoms. So we're going to have 57 plus 23 is 80 atoms. So we have found the number of atoms in the universe in less than 3 minutes. And all that that's required for this is a bunch of bold assumptions. And if you ask an actual astronomer to do this calculation, they're probably going to end up with the same. Maybe they'll say it's 10 to the 81 or 10 to the 79, but it's not going to be too different than this. We have got almost the same answer that anyone else would get. And that's the beauty about estimation. What you get is likely to be something that someone else gets. The difference is likely to be small. So I actually want you to go out and estimate various things, various crazy things. For example, to keep it local, let's find the total number of amount of gas, total gallons of gas pumped in Rochester daily. Now this again, the painful way to do this is to go around and ask all the gas station for their receipts and add it up. And who wants to do that? It's better to just think. So how many people are there in Rochester? Well, let's think about it. Is it about 10 to the 5? That's 100,000. That seems too little. 10 to the 7, 10 million. That seems too much. So 10 to the 6. By the Goldilocks Principle, we have homed in on a decent value here. All right. How many cars per person? Does every single person have a car? Likely not. Is there one car to 100 people? That seems too little. So maybe one car for every 10 people, which means there are 10 to the 5 cars. And this includes cars that come in and out of Rochester on a daily basis. Now, how often do you fill a car? Do you fill it daily? That's too soon. Do you fill it every 100 days? So daily is 10 to the power 0. 100 days is 10 to the power 2. 100 days is 3 months. That's too infrequent. So we'll say we fill every 10 days. You fill every 10 days, and how many gallons do you fill? Well, is it 1 gallon you fill? That's almost a lawnmower sized. No. 100 gallons? No, that's a huge truck. So, yeah, 10 gallons of gas is the Goldilocks zone. Which means if you fill 10 gallons in 10 days, it means you fill 1 gallon per day on average. So 10 to the 5 cars, 1 gallon a day, that means 10 to the 5 gallons per day. And we got this estimate in under 2 minutes without doing anything. So that's the beauty of estimations. Now, if you ask a friend to do this calculation, they may come up with 2 times 10 to the 5 or 3.6 times 10 to the 5, but you can tell them, hey, that's just 10 to the 5.